Okay, this is the lecture video for MAC 1140 Pre-Calculus. This is section 4.6, and we're going to be taking a look at how to find the real zeros of a polynomial function, which has to do with division mainly. The division is going to help us to factor it, and we can use the factors to get all of the zeros, to get the remaining zeros of the function. When you're finding zeros, it means you're finding the solutions. And those solutions, when you're not using division, have come from factoring when it's second degree or higher. So now we're going to use a combination of division and factoring to find all the zeros. And we're going to be employing various theorems as we go along. So since the main underlying property that we're going to be using has to do with division, we're going to start with the theorem for division, and this is the following. This states that if you take one polynomial function and divide by another polynomial function, the answer will give you a quotient plus a remainder. The way that you can check whether your quotient and your remainder are correct is using the following. If you take your quotient and you multiply it by the divisor and then add in the remainder, you should get the original function. That's just the way to check whether or not you divided properly, because the division process gives you a quotient and it gives you a remainder. So doing this is just a way of checking whether you did that division properly when asked to check. We also have a remainder theorem, which comes in very handy in this particular section. And this particular section, it gives us another way, by using the remainder theorem, another way to evaluate polynomial functions. Like we know that always in the past, if we were given a polynomial function like this, we could be told to plug in or asked to plug in some value, and that's called evaluating. So for instance, let's say someone asked us to evaluate at the number 3. The old way that we used to do it, the very first method that we learned is that when evaluating, you just plug in the number everywhere that you see an X and do the operations until you get the final answer. Well, what this theorem says is that if you were evaluating at 3, that's the same thing as dividing by X minus 3, and the remainder that you get is actually the same answer you get when you plug in the 3. So we're going to be employing that remainder theorem as a new way to evaluate functions at a particular value. So instead of just plugging the number in all the way down, we're going to use synthetic division, wait to see what we get for the remainder, and that remainder will be the same as if we had plugged the number in all the way down. Okay, I've given you a couple of examples below so you can try and understand the remainder theorem. Okay, so as I was stating previously, let's say that you were asked to plug in a 3 into this function. You would have to go 3 cubed minus 4x squared, and you would be putting a 3 in there, so here it is right here, minus 4 times 3 squared minus 5. And if you did all of this in your calculator, taking 3 and raising it to the third power, you'd get a 27, and then here you would get, and your calculator would be doing all of this anyway, then you'd be going negative 4 times 9, which would be 36, and then you'd subtract 5, and eventually you would get this answer. But what this theorem is saying is that if you just use synthetic division, and instead of plugging, well, you're going to be dividing by x minus 3. So the remainder theorem says that f of 3 can be calculated by finding the remainder when the function is divided by x minus 3. And since we're using synthetic division, you remember that synthetic division from the previous sections that we've used it in thus far, that you always switch the sign anyway. So the same number that you'd be plugging in here is the number that you would see if you performed synthetic division. So let's say, now evaluate f of 3 by finding the remainder using synthetic division. So when dividing any polynomial by x minus 3. You're dividing by x minus 3. That's the same thing as switching this sign as you get ready to perform synthetic division. And then taking the coefficients from the original polynomial, which are 1 for your third degree term, -4 for your second degree term. You don't have a first degree term, so you have to put a space holder in for the x to the first degree term, and then you would have a -5. So the numbers would look like this. 1 for your first degree term, -4 for your second degree term. You do not have a first degree term in this polynomial, and then you have a constant of -5. So if this remainder theorem is true, we should get the same answer that we got by evaluating the polynomial in a traditional manner, the way that you were first taught to evaluate. Now this is an alternative way to do it. Bring the 1 down for synthetic division, always. The very first column, you just bring the number down and then start multiplying and adding. Multiplying and then adding. And multiplying. 3 times -3 is -9, and then adding. Notice that you get the very same answer that you would have gotten if you plugged in 3 all the way down. Just dividing by x minus 3, which really means that inside the box is always the opposite of this. Opposite sign. But notice that you also get -14 just like you got up here. So that's what the remainder theorem introduces, a new way to evaluate a function at a particular value. Okay, if you are plugging in a -2 to that very same function, that's the same thing as dividing by x plus 2. See, when you talk about the polynomial that you're dividing by, it has the opposite sign of the number you're plugging in. Also, the opposite sign of what would show right here if you were doing the synthetic division. In other words, when the number is still hooked to the x, combined with the x as a polynomial, it has the opposite sign than what it looks like when you're plugging it in the whole thing or when you're doing synthetic division. Okay, so let's try this again. This time we're using synthetic division, and if this remainder theorem holds true, I should get this answer. We are now evaluating at -2, and that's why you see me doing the synthetic division with the -2. Let's make sure that we're going to get a -29. Okay, so the coefficients for this particular function were 1, -4, -5 with the linear term missing, so we have to put a space holder. You know, they're the numbers that we used right here. Still working on the same function. Bring down that 1. Multiply -2 times 1, that's -2. Multiply -2 times -6, that's 12. You're always adding up these columns. Multiply -2 times 12, that's -24, almost done. Add these up and you get -29. So once again, just another way to evaluate a function. You can either actually physically plug it into each and every term where there was an x, or you can use synthetic division. Okay, moving to example 2. And here we get introduced to the factor theorem, and this says that suppose f is a polynomial function, then x minus c would be a factor of f of x, the original polynomial, if and only if the remainder is 0. Maybe rephrase that for yourself so you can understand it. So only when the remainder is equal to 0 have you actually found a factor. You have found a factor of the original polynomial. So by using synthetic division and proving to yourself that what you just divided into the original polynomial resulted in a remainder of 0, that helps you get on your way to factoring the polynomial. And we're going to spend most of this entire section doing that. Of the original polynomial. Okay, so in example 2, it says, if f is a polynomial function and x minus 5 is a factor of f, now here you're just showing that you understand this theorem, which says when x minus c is a factor, well, this says x minus 5 is a factor. If and only if f of the c value, the opposite sign you see is plugged in here. This was a negative c. This is now a positive c. And that's the same thing that they're putting forth to you right here. If x minus 5 is a factor, then f evaluated at positive 5 must be equal to 0. So you're just showing that you understand that. Here they're giving you specific numbers. Here they're just using a generic c. The c value was this negative 5 while it was in polynomial form, and then it switches signs just like this theorem says, but you're just completing the theorem by filling in that 0. Now we're going to actually get a chance to use the theorem in example 3. So it says, use the remainder theorem to find the remainder when f of x is divided by x minus 2. Then use the factor theorem to determine whether x minus 2 is a factor of f of x. Okay, so it says that we are dividing by x minus 2. So remember, when you're doing synthetic division, when you start to work on the problem, you always switch the sign before you get ready to do that synthetic division. So it may appear as a negative 2 when it's still being combined with the x as a polynomial, but when you deliver the number to this box, you switch the sign. Take the coefficients and stretch them out horizontally. So third degree coefficient, second degree coefficient, first degree coefficient, constant. Okay, when you're doing synthetic division, you drop down that first number, then multiply and add. Add these up, you get 5. 2 times 5 is 10. Add these up, you get 6. 2 times 6 is 12. Negative 6 plus 12 is 6. So this is your remainder in the last column. Now, since the remainder is equal to 6, that means x minus 2 is not a factor of f of x. Because if it was a factor of f of x, you would have gotten a remainder of 0. So x minus 2 is not a factor of f of x since the remainder is not equal to 0. Okay, let's continue, and we'll come across plenty of problems where we do get a remainder of 0, and then that's going to help us go further with the problem, because if you do get a remainder of 0, you have found a factor, and that helps you further factor the problem. Okay, some of the other theorems that come into play as we try to work with synthetic division and find the various other operations that we can do with it are the following 2 theorems. A polynomial function cannot have more real zeros than its degree. So if it's third degree, it has at most 3 real zeros. Then the rational zeros theorem we're going to be using quite a bit. And if you remember this from the previous course, MAC1105, where it was introduced, and then also it would have been introduced in an Algebra 2 course if you took this in high school. And in those classes, they talk about how you make the list of rational zeros that you're going to attempt to use using synthetic division. And any time that you get a zero as the remainder, so you're using these theorems in conjunction with each other, then you know that you have a factor. So let's start at the very beginning. Okay, this says list the potential rational zeros. Let me explain those words. Rational means you're going to come up with a list of fractional, that's what rational means, fractional zeros. These are potential solutions. Zeros means solutions, the solutions to the polynomial. So you just have to understand that rational means fractional. We're going to come up with a list of fractions. These fractions are all potential solutions to the problem, and we are going to be trying each one of them using synthetic division. So yes, synthetic division is still the mainstay of this particular section. We're just dragging in these other theorems to assist us with what is the purpose of synthetic division. And it's pretty strong. It can be used to do a lot of things. So first let's teach how to get this list of possible solutions, also known as the list of potential rational zeros. Okay, so according to this, all of them will be fractional in their form. The top, the numerator, will be called P, which is really just the factors of the constant. This guy right here. Factors of the constant. Those will make up all your numerators to these fractions. You are to consider in your list both the positive and negative versions of these fractions. The Q are the factors of the leading coefficient. So you're going to see me do this quite a number of times. Factors of the leading coefficient before we start using it to go on with other types of problems. Okay, so this is where we're going to get our P values right here. This is the constant. And luckily this is a 1. The only way you can factor a 1 is 1 times 1. So the less factors you have, the better off you are because the less possibilities you have. On the other hand, the Q's, they come from the leading coefficient. And again, since this is a prime number, it doesn't factor in any way other than 1 times 5. So now when you make this list of possible fractions in the form P over Q, where these P values will represent the numerator, these Q values will represent the denominator. You can list them like this. Okay, so the only number we have as a numerator is 1. So we can either go 1 over 1 or 1 over 5. And that's all we have in our list. Sometimes the list is very long. It's just that we don't have that many factors here, nor do we have that many factors here. So this particular list is short. So if you wanted to list these individually, one of the values inside here is positive 1. Another value here is negative 1. Positive 1/5, and you don't have to write the positive in front of your positive values, and negative 1/5. This is if you wanted to list them separately. This is just a condensed way to learn to list them, meaning that each of the values in here, that the positive version of that value as well as the negative version is a potential rational solution. And when we do get as far as using them, using synthetic division, we're going to be considering either the positive or the negative value. Okay, now this said just make the list, do not attempt to find the zeros, because if you were going to find the solutions, it would be from this list. You would try one of them at a time until you get down to second degree, and I'll say more about that in the next few problems. and then I would just factor it from there. That'll be quicker. Okay, so now let's see, we are on example 5. And in example 5, it says use the rational zero theorem to find the potential real zeros of the polynomial function. Use the zeros that you do find to factor the function over the real numbers. So the key is to get down to second degree, because we've spent a lot of time talking about how to factor second degree polynomials. So you might as well just factor because let's think about this. What if you made a list of potential zeros and there were 10 items in them, and the first one works, which every time you find a zero, it brings you down a degree. So let's say the first one works, you get down to second degree, and then you go back to the list and you keep trying those values one by one until you find the next thing that works. What if the next thing that works is it doesn't occur until all the way at the end of the list? Then you have sat there for 10 minutes trying all these numbers, whereas if you just stop once you get to second degree and factor, you save a lot of time that way. So we're going to do it that way. And that's what they're asking you to do here anyway. Okay, so list the zeros. And we're also going to list the factors in this problem. Okay, first thing we're going to do is list the potential. See, we don't know that anything is actually a zero until we do synthetic division. But our possibilities, our potential zeros, which come in the form of rational expressions, fractions, are written like this. Okay, don't forget, this is where we get the p-values. 77 can factor as 77 times 1, but it can also factor as 7 times 11. So these are all potential numerators of these fractions that we're going to create. The p-values represent your numerators. And we're going to make a list like this where we form all these fractions, p over q. So the p-values come from the constant, and they have to do with the factors of the constant. Then right here, whatever the leading coefficient is, that's where you get your q values, and they are what help you form your denominators. Okay, so here we go, we're making our list. Throw that plus or minus in the front, and we're going to I'm going to start with these numerators. I'm going to go from the smallest one to the biggest one, each time placing it over our only denominator, because the factors are what the q's are, and 1 only factors as 1 times 1. So this is the only thing, the number 1, that we can use as a denominator. Okay, so it's going to be 1 over 1. That's one of the values that is a potential zero. Or I'll do the next biggest one, 7 over 1. Next biggest one would be 11 over 1. And then the largest one would be 77 over 1, always using these as the numerators. Now I'm saying the fractions verbally. This was really 1 over 1, but anything that's over 1 reduces to whatever is in the numerator. This was 7 over 1. I've already reduced it. This was 11 over 1, and then this last one is 77 over 1. Okay, so now this first question says, what are the actual zeros? That's what this really means. List the actual zeros. These are the potential zeros. So now I'm going to try these one at a time. So remember, when I try that one, I can try positive 1 or negative 1. I don't know which one of those is going to work. It might not be either one of them. I'm going to go from the smallest to the biggest just because the arithmetic will be easier. So here we go. First thing I'm going to try is positive 1. Okay, you take the coefficients and stretch them out horizontally. Let's see if any of the powers are missing. Third degree, second degree, first degree. No, we don't have any powers missing, so just take those coefficients and stretch them out horizontally. So it's 1, -3, -81, and -77. Okay, you're going to bring that first number down. 1 times 1 is 1. Add them up, and you get -2. 1 times -2 is -2. Add these up, and you get -83. And I think you can see already that this is not going to zero out. You're not finding a 0 unless the remainder zeroes out. And you can see that that is not going to happen. Okay, and we can check that arithmetic real quick. We brought down the 1. We went 1 times 1 is 1. Brought it up here, added these up, got -2. 1 times -2, brought it up here, got -83. 1 times negative, so you see this is, you're not going to zero out there, so you might as well just stop. Let's try again. This time we'll use -1. Okay, so you have -1. Let me write a little bit more clearly because last thing we need is examples that we can't read. Okay, so that's -1. Take the coefficients and stretch them out horizontally again. And let's see if this one works. The 1 didn't work. Okay, so bring down the 1. -1 times 1 is -1. Add these up, you get -4. -1 times -4 is 4. You get, when you add these two up, you get -77. -1 times -77 is +7. And there you go. We have found a 0. When it zeroes out like this, that means that this number right here is the actual 0. Okay, so this is, we already have one of the answers. And remember, this is 3rd degree, so the maximum number of zeros we can have is 3 of them. If it was 4th degree, the maximum number of zeros or solutions, if that's what you want to call them, that would be the maximum number we can have. It's determined by the degree. So I've already found one of the 3 solutions. Okay, now we're going to go on. But what I suggest is instead of returning to this list and trying 7, then -7, then 11, then -11, because you don't know how quickly you're going to find this. For all you know, the next answer could be at the end. So to avoid a lot of work, let's do it this way. Each time you find a 0, you have done what's called decompressing the original polynomial. This was the original polynomial right here. It was 3rd degree. By the time you find a 0, you have now brought it down by 1 degree. And you can go ahead and put those variables right back on there. This is your 2nd degree term, not that you need to put that 1 there. This would be your 1st degree term, and this would be your constant. And that is equal to 0. And you could just factor your way to the other 2 answers. So that's 2nd degree, and if we factor this, we can get 2 more zeros out of this, or what we call 2 more solutions. Okay, so take the square root of that. Then ask yourself, what 2 numbers could we multiply? Because this is a trinomial with a 2nd degree, 1st degree. It's a quadratic trinomial. So when we try to figure out what goes in the back position of each of these parentheses, we're just looking for 2 numbers that multiply together to give us -77, but that add together to give us -4. Okay, and that would be 7 and 11. We have to make sure to get the negative on the right number. So if we let the larger number be negative, and the smaller number be positive, then when we add these, that sum will be negative. Okay, same thing here. The -11 and the 7 work. This times this is -77. This plus this is -4. So there we go. We have this all factored. A -11 and a +7. When it's in factored form, the zeros are the opposite. In other words, what makes this 0? +11. So there's another 0. And put it up here. And then what makes this 0 would be -7. So that is our third answer. So all three solutions, or what we call zeros, are right up here. And then if you want to list them in factored form, well, you can already see what they look like in factored form. When they're in factored form, they have the opposite sign of what they have when you're reporting them as zeros. So we've already found out that -1 was a 0, but we found out that that was a 0 through a different way. We found out that it was a 0 by doing synthetic division. Here, we found the zeros by factoring. We used these factors, and then we looked at each of the factors and asked ourselves what would make this 0, because those are the other zeros. So we just found the zeros in different ways. This was the first one, but in factored form, it would look like this. Okay, here we have the other two factors. I mean, the solution is +11, but it looks like -11 when it's in, but it's a -11 when it's in factored form. Here was the answer -7, but it's a +7 when it's in factored form. So there is everything that they requested. We made a list of potential zeros for this problem. We began by trying 1, it did not work. Then I tried -1, that worked. It actually zeroed out the polynomial, and therefore it is called a 0. But it can also be written in factored form with the opposite sign. Then at that point, once we zeroed out, we had decompressed the polynomial. We had a new polynomial, but now it was second degree. We put the variables back on it, factored, and from those factors, we found the other two solutions. Okay, let's move on to number 6. Okay, give me a minute. Okay. All right, so now we're going to do the same thing in example 6, just so you can solidify this process. This is the main point of this section. Okay, we're going to try and make this list of possible rational zeros. I'll just put the plus or minus out here. Okay, let's see. This is going to give us our p-values, our p's. Those will be the tops of the fractions. And this is where we're going to get our q's. And those p's and q's come from the factors. So let's see, 28 can be factored as 7 times 4. It can also be factored as 2 times 14. It can also be factored as 1 times 28. So we have 6 different things that we can use as our numerator, our p-value. 2, luckily that's a prime number, so that only factors as 1 times 2. Okay, here we go. I'm going to start with the smallest number here, each time placing it over the 1. And when I get done placing each of these numbers over the 1, then I'll place each of these numbers over the 2 to see if there's any brand new values. Okay, here we go. I'm always going to go from smallest to biggest. So smallest one first, 1 over 1. That's just 1. Next one, 2 over 1. Okay, I'm using this as my denominator right now. These can only play the role of the numerator. So next value, 2 over 1. Okay, next value, 4 over 1. Next value, 7 over 1. Next value, so I did 1, 2, 4, 7, 14, and 28 remain. Okay, let's start again with the smallest number, but this time it's going to be over 2. So this time we're done with that. Now we're using the 2 as a denominator, and see if this adds anything new to the list. Let's make this bigger. We got a 28. Okay, so it's now 1 over 2. That's new. I don't have that in my list yet. Then I can do 2 over 2, which is 1. I already have that, so forget that. Then I can go next biggest, 4 over 2, which is 2, and I already have that, so I don't need that again. Then I can go 7 over 2, that's new. I don't have that in my list yet. Okay, then I can go 14 over 2, which is 7, and I already have that, so that's not going to do me any good. Then I have 28 over 2, and that's 14, and I already have that. So that finishes the list. So somewhere in this list are all 3 answers, if there are 3 real zeros, because the most you can have is 3 real solutions for this particular polynomial, being that it's 3rd degree. And I am going to try and find the first one through synthetic division, but I don't think I want to go through all these numbers in the list. Too much work. So once I find the first one and I bring this polynomial down to 2nd degree, I'm going to factor my way to the other zeros. Okay, so here we go. First thing I'm going to try is 1, but don't forget, it's +1 and -1 that's in this list. So as soon as you get done trying the 1, if it doesn't work, try the -1. So here I go, 1. The numbers that I'm going to string out are 2 for 3rd degree, -4 for 2nd degree, -14 for 1st degree, and then 28. So this is 2, -4, -14, and then 28. I'm going to bring this down. 1 times 2 is 2. Add these up, I get -2. 1 times -2 is -2. I get -16, and you can see that this is already not going to work. Once you see it's not going to zero out, abandon, go to the next number. Okay, again, string out those coefficients. You know, 2, -4, -14, and 28. Okay, drop that first number down. -1 times 2 is -2. Add these up, get -6. -1 times -6 is 6. When you add this, you get -8. You can see this is not going to work either, because that's not zeroing out. Let's go to the next number in the list, which is 2. I'll try +2. If I need to, I'll go to -2. Okay, so let's see. The numbers again were 2 for 3rd degree, -4 for 2nd degree, -14 for 1st degree, and then 28. I'm going to drop down this 2. 2 times 2 is 4. Add these up, get a 0. 2 times 0 is 0. Add these up, get a -14. And here we go, right here we got one. 2 times -14 is -28. It has zeroed out. And because it's zeroed out, that means this actual number that caused it to zero out, this is the actual number that is the 0. So 2 is a 0. At the moment that you zero out, you have brought it down a degree from where it was when you began. So if it began as 3rd degree, you are now at 2nd degree. So just put the variables back on. This would be your 2nd degree term. This would be your 1st degree terms. You now do not have a 1st degree term, and this would be your constant. And what you want to try and do here is continue factoring. Continue the problem, but by factoring rather than going through this list. Because if you wanted to, you could keep going with this list until you find the answers that this is going to give anyway. Okay, so when you factor this, it is 2. You can take out a GCF first just to make the rest of it easy. X squared minus 7. Okay, and then continue factoring. You could go, you can treat this as the difference of squares. I mean, if you wanted to say, I know 7 doesn't have a square root. That's an integer. It doesn't have a perfect square, but you could just say that you can take the square root of this, and that square root would be x, and you can take the square root of this, and it would just be reported as the square root of 7. So if you wanted to continue factoring this, it would be The 2 that you pulled out, that's one of the factors. It's just a variable. It's just a number rather than a variable. And then this, treated as the difference of squares. And the way you factor that is you take the square root of this, which is x, and then you take the square root of this, which you can write like this. Square root of 7 is written like that. Square root of 7 is written like that. And remember, when you're factoring the difference of squares, one sign is a plus, the other one's a minus. So in completely factored form, and we can finish this list of zeros and then we can talk about the completely factored form. So one of the zeros that we found was this 2. It's already up there. And then the other zeros, you can just look at these factors that we just created. This is a factor, and they were the factors of what remained right here. So what would zero this out? If this was a negative square root of 7, if someone came in here and plugged in negative square root of 7, added to positive square root of 7, that would zero it out. So your next zero is negative square root of 7. And then your third zero is, what could you plug right in here to zero this factor out? And that would be positive square root of 7. Doesn't matter which of these two. Then taking all of the zeros and writing them as factors, you have this factor that comes from the 0, positive 2. But remember, when they're in factored form, the sign switches. You have this 0 of negative square root of 7, so it'll look like this when it's in factored form. And you have this 0 called positive square root of 7, so it'll look like this when it's in factored form. Then also, don't forget, when you were factoring here, how you pulled out a 2 when you were in the process of factoring, that has to be reported in your final factored version, because all of this, when multiplied together, should equal the original polynomial. And that 2 that we yanked out right here, we had a common factor of 2. That is part of what would get you, if you multiplied all of this, that's part of what would get you right back to this original polynomial. So you can't leave out any GCF that you might have taken out, which was this. Don't forget to report that in your factored answer. Okay, that's example 6. Okay, moving on to example 7. Now we're going to 4th degree. So that's a little bit more work because you're going to have to bring this down twice. You can't factor it. I mean, you could try and factor it before you get there, but most of these problems will not factor until you get them down to 2nd degree. It's not that it's not possible to factor at 3rd degree. I mean, once in a while you'll be thrown a problem where that's possible. But we're going to bring this down twice. We're going to keep working this problem from the potential list of zeros until we find 2 zeros. Once we get down to 2nd degree, we will factor it to find the remaining 2 zeros. So let's work on that list. Remember, our p-values come from the constant, and it comes from the factors of the constant. This can be factored as 9 times 2, 6 times 3, or 1 times 18. So all of these, any of these 6 numbers can serve as the numerator of this fractional list that we're forming. Okay, and then luckily the leading coefficient is only a 1. So our q values can only be, I mean, the only way you can factor a 1 is 1 times 1. So the only possible thing that our denominators can be is 1. Okay, these q values are always the denominators of these fractions. You can see the q on the bottom there. And the p's are always the numerators, as you can see right here. Okay, so here we go. I'm going to start smallest to biggest. So I'm going to use this one first. It would be 1 over 1 or just 1. Remember, plus or minus does apply to anything in this list. Then I could go 2 over 1 or just 2. Then I could go 3 over 1 or just 3. So I use that, I use that, I use that, then I can go 6 over 1. And I can go 9 over 1. And I can also go 18 over 1. So I've used everything that I could possibly use as a numerator over 1 each time. So my 4 answers can be in here, but there are actually 1, 2, 3, 4, 5, 6, 12 things in this list. Because there's positive 1 and negative 1, positive 2 and negative 2, positive 3 and negative 3, etc. So it's easier to just try to bring it down twice, find 2 zeros through synthetic division, and then once you get it to second degree, we'll factor. Okay, here we go. I'm going to start off with 1. I'm going to try the 1 first. Coefficients here are 1 for 4th degree, 1 for 3rd degree, negative 11 for second degree, negative 9 for 1st degree, and 18 for 0 degree, the constant. Let's see if this works. And bring this down. This is a 1. 1 times 1 is 1. Add these up, get a 2. 1 times 2 is 2. Add these up, get a negative 9. 1 times negative 9 is ooh, I think we got one. Negative 18. 1 times negative, yep. We already have one. Okay, so check. Since that zeroes out, that means we have already found one of the answers. So I'll put that right here. Okay, still 3 more answers to go. So with these problems, when you're going to continue to use synthetic division to find zeros, you need to work on this string right here. You need to continue working on this string. I shouldn't put that there because I am going to continue working on it. And therefore, the next thing in the list, I'm going to put it right here. Okay, so I tried 1. I'm going to try negative 1. Before I move on to 2, I want to try the positive and the negative version of this first number. So now I'm going to try negative 1. Let's see if it works. And this string that I'm working on right now, keep working on this string until you find the next zero. Don't go back to the original because you're just going to be, you're just going to have the same problem over and over again where you're going to have to find the second zero. You continue to work on what remains below the line. And if it doesn't work, what I'm going to try right now, then go right back to this list of numbers and try it on another number. Okay, so here we go. We're trying the negative 1. We drop this down. Negative 1 times 1 is negative 1. Add those up, you get 1. Negative 1 times 1 is negative 1. Add those up, you get negative 10. Negative 1 times negative 10 is 10. Add those up, you get negative 8. Forget about this column. This did not zero out, so forget it. We have to try again. Now we're going to move on to 2, but use this same string. We did not find another zero yet. Because right now what we've done is we started at 4th degree, and by the time we got this first zero right here, we were at 3rd degree. We need to get down to 2nd degree, so we have to find another zero. Continue working with this string. I'm going to write it again right down here. 1, 2, negative 9, negative 18. You don't need that zero anymore. Next number in the list that I could try is 2. Okay, so let's see. Bring this down. 2 times 1 is 2. Bring it here. 2 plus 2 is 4. 2 times 4 is 8. Add these up and you get negative 1. Nope, this is not working. Scrap that. Again, go back to the last time that you actually did get a zero. You're still working on that string. So let me put a box here for the next number that I'm going to use, which I used 2. Now I'm going to use negative 2. And that same string. 1, 2, negative 9, negative 18. Let's see if this zeroes out. So this times this is negative 2, I got a 0. This times this is 0, I got a negative 9. This times this is 18. And there we go, we got another 0. So just like you were at 3rd degree right here, now that I have zeroed out again, that means that now I'm at 2nd degree. Each time you zero out, you bring it down another degree. That's called decompressing the polynomial. So we now know that we have two zeros here, two solutions thus far. We have the 1 that we found right here when it's zeroed out. We have the -2, that's a solution because it's zeroed out. So -2 is an answer, but this is 4th degree, so we still need 2 more answers. But I'm going to work right off of what I now have. I'm down to 2nd degree, so this is 2nd degree with a coefficient of 1. There is no x term. It's -9, and all of this new 2nd degree polynomial is equal to 0, and this is factorable. Okay, this is the difference of squares. And it can be factored by just taking the square root of the first term, putting it in the first position of each parenthesis, then taking the square root of the second term and putting it in the second position of each parenthesis while alternating the signs. And right from those factors, you can see what the zeros are. What would zero this out would be x equal to -3. And what would zero this factor out would be x equal to +3. So we have just found the rest of the zeros. Okay, so there they are. This 4th degree, I already have all 4 answers. I got 2 of them through synthetic division. And I got the other 2 by factoring. Okay, don't forget you're also supposed to give them the factors that go with these zeros. Remember, the factors bear the opposite sign. So if one of your answers is a +1, then in factored form it looks like this. If one of your answers is a -2, then in factored form it looks like that. Likewise for these other zeros. What corresponds to a 0 of -3 is a factor of x plus 3. And what corresponds to +3 as a 0 is x minus 3. So again, these have the opposite signs as those. We've done 3 problems like that. 2 of them were 3rd degree, and then this last one was 4th degree. And I demonstrated how to bring this thing down twice until you get it to 2nd degree. And then you can jump off into the factoring. Okay, our last theorem is called the intermediate value theorem. And what this theorem says is that if you have one value that is less than another, and this has to do with the polynomial function that they're asking you for. Here, this would be the a value, and this would be the b value. You can see that that a value is less than the b value. So that's this part of the theorem. So now what they're saying is, if when you evaluate this function at the a value, that's what they're talking about right here, and you also evaluate the function at the back value, the b value, and if those come out to be opposite signs, that means that there's at least one 0 in between -2 and 0. Okay, so first you have to start off with one value less than the other. You're going to evaluate at the lesser value, which is -2. And that would be 16 times -2 to the 4th. Minus 7 times -2 to the 2nd, plus 8 times -2, minus 1. Okay, so let's see what this is. We can just put it in our calculator. This is 16. 16 times 16. You can just stick it in straight like that. 16 times 16. I'm just doing some of it in my head. Okay, and then this would be 4 times -7. And then this is -16 and -1. Okay, so for this I got positive 211, and now I'm going to evaluate at the bigger value. 0 is bigger than negative. This one will be easy though because there's zeros, so it's going to wipe out all these terms where I'm plugging in the 0, the first, second, and third term. So all that's left is just negative 1. Okay, and you can see that these are opposite signs. And again, what this theorem says is if you start off with a polynomial, you're being asked whether there's a 0. Is there a solution between -2 and 0? That's what this theorem's about. And you can do that by just first investigating for the interval that they've asked you, is there a solution in that interval? Make sure that one number is less than the other. That's easy enough to check. Then evaluate your polynomial at the smaller value and not evaluate at the larger value, and make sure that these come out to be opposite signs. And if they do, that checks off the second part of the theorem. So that means, therefore, that's what 3 dots shaped like a triangle means. That means therefore, the function f of x has at least one 0 one real 0 has at least one real, I left a word out there, one real 0 between -2 and 0. You can find at least one real solution. Zeros mean solutions. Okay, that concludes the examples for section 4.6.